When we look up at the night sky, the universe feels eternal. But those billions of burning stars are just a brief spark in an overwhelmingly long, dark timeline. Eventually, every light blinks out. The engine driving this decay is the second law of thermodynamics. It dictates that the entropy of an isolated system always increases. The universe is sliding toward chaos, moving from concentrated energy into randomized dissipation. Because this process only runs one way, you can't unscramble an egg, it forces time to point in one direction, the arrow of time. This chart shows a cross-section of the universe from the Big Bang to the present day. You can see the widening shape of this cone representing the cosmos actively stretching apart, proving that our timeline is already accelerating the dispersal of matter. So if our cosmic clock is driven by this relentless combination of entropy and physical expansion, we have to ask what reality actually looks like when the clock finally runs out of energy to tick. The era we live in now, full of active, hydrogen-burning stars, will end in roughly 100 trillion years. The massive gas clouds required to forge new suns will be completely exhausted, bringing the birth of new stars to a permanent halt. As the last red dwarfs quietly burn out, the cosmos enters the degenerate era. The only surviving astronomical bodies will be dense, dying remnants: white dwarfs, brown dwarfs, neutron stars, and black holes. These stellar corpses are incredibly cold, but they aren't completely dead yet. They manage to stay fractionally warm by gravitationally pulling in weakly interacting massive particles, the stuff we call dark matter. As these particles accumulate in the stellar cores, they collide and annihilate, generating a faint final source of heat. Once the local reservoirs of dark matter run dry, the universe hits a profound scientific crossroads. The entire physical fate of the cosmos then rests on a single unknown factor: the stability of the proton. Many physics models predict protons are unstable over massive timescales. Across 10 non-nillion years, the protons making up all remaining baryonic matter, including dead stars and planets, will slowly decay. They break down into lighter particles and eventually flash into radiation. On the other hand, if protons are perfectly stable, matter takes a different path. Over unimaginably long stretches of time, rare quantum tunneling events will cause all remaining matter to fuse together, compressing into heavy, dark, and entirely inert spheres of solid iron. Whether matter completely evaporates into stray photons or freezes solid into iron stars, the outcome is the same. Every complex physical structure left over from our current era is mathematically guaranteed to be erased. Push the timelines forward to a Google years. That's a 1 followed by 100 zeros. At this point, black holes are the sole remaining organized structures in the entire universe. But even these massive gravitational anchors are not immortal. In 1974, physicist Stephen Hawking proved the extreme physics near an event horizon forces black holes to slowly leak their mass back into the void. Empty space is filled with quantum fluctuations, virtual particle pairs that constantly pop into existence and annihilate. Hawking showed when this happens on a black hole's edge, one particle is pulled inside, while the other escapes, draining a tiny fraction of the black hole's mass energy. As the black hole shrinks over eons, this radiation increases. Its temperature spikes exponentially until the final microscopic remnants dissolve in a sudden, violent, and completely invisible burst of gamma rays. That agonizingly slow evaporation assumes a standard expansion of space. Theoretical physics offers a few violent wildcards, the most dramatic being the Big Rip. If the dark energy accelerating cosmic expansion grows stronger over time, becoming what is known as phantom dark energy, the stretching of space will outpace forces of gravity and electromagnetism. It rapidly tears apart galactic clusters, then stars, planets, and finally the subatomic particles themselves. Whether the universe suffers a sudden subatomic tear or quietly waits out the evaporation of the last black hole, the arrow of time points toward a completely empty void. Following the evaporation of the final black holes, the cosmos arrives at its ultimate resting state, the heat death. In this stage, The few stray photons and subatomic particles left in the universe are stretched across massive distances. The temperature drops to just a fraction above absolute zero, settling into a state of absolute thermodynamic equilibrium everywhere. Without any temperature differences or pressure gradients left in the system, physics hits a wall. There is no longer any mechanism to transfer energy or perform physical work. This forces us to confront a difficult question about the nature of reality. By definition, time is a measurement of change, a way to sequence physical events. In a universe where energy is perfectly dissipated, nothing can ever interact, alter, or happen again. The progression of time, for all functional purposes, simply ceases to exist. Yet modern quantum mechanics suggests one final twist. Absolute nothingness might not be perfectly stable, especially when given an infinite amount of time. In a true infinite timeline, statistical probability dictates that random quantum fluctuations will eventually produce a sudden, massive decrease in entropy. Out of the frozen, empty void, the exact right configuration of energy could spontaneously erupt, triggering an entirely new Big Bang. The laws of thermodynamics chart a cold and inevitable end for our current universe. But the death of time itself might just be the necessary spark to start a clock we can't yet fathom.